Good afternoon, everyone. We have with us today our speaker, Dr. Supratim Gupta, who did his PhD from IIT Kharagpur and is currently working as an assistant professor at NIT Rourkela. His research area focuses on development and analysis of signal, image, processing, and computation techniques using algebraic and probabilistic theories and their implementation on FPGA or system on chip. He is principal investigator for the project Reconfigurable Hardware to Detect Drowsy Operator from Eye Image Under Spectacle, sponsored by Board of Research in Nuclear Sciences, Government of India. He is also a co-principal investigator for design, development, and prototyping of state-of-the-art hybrid energy storage systems based on high-power, high-speed electric vehicle drivetrain for a multi-utility vehicle, which is sponsored by Department of Science and Technology, Government of India. More importantly, he is the person who introduced me to research and taught me how to systematically and consistently pursue the research topic. My fundamental research topic of image quality assessment that I started in my MTech and continued as my PhD research topic is because of his guidance. I request you, sir, to take over the session.
Okay, thank you, Vipin, uh, for this welcome. And I think we can start the presentation right away.
Yes, sir.
So, is the screen visible to you all?
Yes, sir, it is visible. Sir, can you change slide and check because for last few speakers, the slides were not changing
Okay, so
on our side.
let's see. Is it changing?
Yes, sir, it is changing.
Okay. Okay, good afternoon to everyone. So, today we will be discussing on face detection and particularly from feature extraction to today's trend with convolution neural networks. And that too, I will try to show you that how we can develop those systems on the system on chip like say Xilinx Zinc, which we have done here in NIT Rourkela. So face detection in particular, but if we generalize it, we'll observe that it can come under the object detections. So and then the one question remains here always that what is the best description of a face, human face particularly. So we'll be discussing those, that how we can describe what is meant by feature and then how we can extract that and then whether we can do it automatically or adaptively or not, that we'll be observing. But let us be motivated that why we should go for face detection, and we should able to find some applications of them, like we can go for fraud detections which may come under say face recognition. So we have to have the face detection before we recognize that particular face. We can go for the biometrics using the faces, facial features, the eye features. We can also go for healthcare systems or advertising system. Apart from that, we can also go for say communications, maybe particularly non-verbal communications with psychological or you see uh, bio behavioral analysis. So we can do all those if we can first identify or extract the face from the image. So we'll start with a fundamental problem of any signal processing technique, which is called denoising. So we can imagine that someone in crowd is calling to his friend, and then there is a background noise which is getting degrading that particular sound of that person, and then so all these noise can be summed up into one model called the Gaussian noise model, and that is added with this YT and produce this YT, which is means heard at this receiving end. Now, each of these signal sample, if we observe here that at a particular instance, we have both the signal xt and the eta t. Okay, and so if I assume this ht as the identity operation, okay, so that means we get this at xt, and so this is essentially to get this xt out of this yt observation, we get the denoising problem solutions of this denoising. Now we will define, or we will try to visualize the same situations, that a particular sample is a combination of xt as this each sample yt as a bag of signals. Instead of it is a arithmetic operations between this xt and eta t, we have a collections of that xt and eta t to produce this yt at this end. So at this end we have this yt, which is noisy. And so with this concept, we can find that the essentially the inverse operations of this, that means we want to get this xt from the observation yt, is we'll be calling the basic processing unit called filter. Okay, and we have very often denoted this like hn or something like that, and then we have this hn can be a vector, and so we can have number of such coefficients, say h0, h1 up to some hm minus 1, like that. Now our objective always been to find this h0 to hm1 with certain given input output examples. Now, as I coined this means concept, that is a YT is a bag of signals or collections of signals. So let us have these signals where we have a collections of phase and non-phase data, and then what with the filter with this filter we want to do, we want to segregate. That means some of the images we want to discover as a noise bin or non-phase bin, or some of the images we want to allow to be in the phase or signal bin. And so essentially what we have done a classification, but this is exactly the extension of the denoising problem. Okay, so we do not know what is inside this bag, but we select it and allow some bins, some images to be in phase bins or signal bins, or some images we are discarding, rejecting rather. Okay, so in classifications of images, we have this problem that we want to identify a particular object. So I showed you with the started with the face, but that is also applicable to different other objects, right? And then we can observe that we have identified that this image contains that particular object. This is classification problem. But we also want that this classification means where this particular object is there inside the image, and essentially we'll be calling it as a localization problem. So if we combine this classification and localization, we'll come up with a solutions to particular problem, like whether the object is there as well as where that object is there. Now, once this is for object and no object situation, we can have different other objects different from these particular images or image which it contains. Now, what we want, that we want to identify all these different objects, and essentially this is a multiple classification problem, which again object detections. But what essentially we have observed here, that the simple denoising problem, the concept can be extended, and then we end up with a classification problem in the images.
It is yours.
And so uh, I think someone is not muted, so it would be better if it is muted. So we'll see that how we can do this classification. So how we can find that whether this pixel value itself, so we can have the pixel values which can distinguish between like these little pixels and the pixels of this dark. Okay, so they are different. So with that pixel value, so the pixel can differentiate between two objects. Okay, or we can have say some edges and that particular shape can identify the different objects or differentiate between different objects, right? So this, while this we can call it as an edge, so this edge can differentiate between that, or the pixel itself can differentiate between these two objects, and so we can say that this is a description or descriptor of the object that differentiate between different objects. Okay. So that descriptor will be calling it as a feature, and then we'll try to understand the feature at multiple levels. Like we want to describe this image and how we can describe this image. So if you have any experience with transforms, like say Fourier transform or say eigen transforms, so you can see in all these cases what we do, we try to represent a function as a linear combinations of some atom. Okay, so this we can call as atom, or in case of Fourier transform, the functional case basis function, or in certain case these are the eigenvectors, or so. And so now we'll be observing that say some edges oriented in this direction or this direction or this direction. So I can linearly combine all these and with channel search, with free channels. Now let us see alternative one. I can also take parts of the faces, and then I can linearly combine all those faces, all those parts, and I can generate this image itself. Again, I can further combine all these basic blocks or parts of the faces, join together, get a full face. But now I have multiple such faces, and we can again find these faces. Say for example, this face is, so this is our face A, and in this dictionary we have that face A, right? So what I can find, that I can find that FA as 1 into that FA from the dictionary, plus all these are 0 into all sum of these bases, right? And so I can represent this face image in this dictionary with one coefficient for this particular face, and the other coefficient should be 0. So we can represent that as a vector which says 0, and somewhere that 1 will be there and remaining coefficients will be 0, and that we can say this is FA, where this position is for FA from the dictionary location. Okay, so essentially what we are trying to represent a signal or image with the descriptors or features at different levels. Now, why we go for different levels? Because it will ease our representations. For example, if I use these lower, this face image edges, and then try to represent, I will find that same FA can be having some non-zero values more than these. Okay, so these are non-zero values. So the representation will be dense, while this the representation with these atoms will be sparse enough, and that will help us to speed up as well as to reduce the use of resources to be minimum. Okay, and speed to increase the speed of our computation. So we can observe that this is our image, and this vertical edge, these are the features of that image which can describe the vertical edges in that image and its locations, also the horizontal image in this. And if I combine these two and have these informations of the color or grayscale, we can regenerate or synthesize this image once again. So essentially I can say this is a function which is taking this image I and generating, say this is function V, generating this image, and we call this as a feature. Then similarly we get this function H and we generate these horizontal edges. So essentially the feature we can say as function of some image or the signal. Now, if this function becomes identity, then it implies that this feature is the pixel value itself in case of image, right? So we can consider that as this. So now we can have a general or abstract visualization that if we want to filter it out, so what is needed, we need to convert this input image into some representative form. Here we have just taken the RGB channels values, the pixel values, and converted in a vector, one single vector. Now if we have, say, m cross n size of this image, so we'll have this vector as mn cross 1. Okay, and then we take all these pixels, do some operations on these, and generate some value, here say y, So it can be 1 if this image contains the face, or it can be 0 if this image does not contain this face. Now there are some issues we can highlight here. What is the nature of this function? So we can highlight whether it is a linear operator or it's a non-linear operator. So this is one issue. We need to understand that how can we, if it is a linear operator, then how can we implement that linear operations? If it is a non-linear operator, then how can I implement that non-linear operations? And why do we need the linear operations or non-linear operations? So majority of the cases we can find that the signals which are getting processed and perceived by us or the machine, so those follows a non-linear operations. And so very often we have to go with non-linear operators or so, but sometimes we also can observe that we can linearize that non-linear processing, natural processing within a very short span of that particular variable or space, and then we can have a linear operator on that. Okay, so our problem, so we can think of that if we have a set of face and non-face images, the bag of or collections of them, but along with that we have also labels. That means that at priori this F we are collecting with this known input and known output, right? And then we want to know what is this function which will give us the if I give the input x, it will always produce this y, corresponding y. Okay, so we can think of that this function is producing some values, but this may not be the value which is given in this collection with that label. So we find the error between that given label and the generated label, and then we again use a function of that error, and then we try to minimize that error, and that particular conditions will produce that if, which we have said just now, that it can be Hn, and essentially say this H0, H1 up to say Hm minus 1. So we want to know for what values of these Hi's this particular function of this error will be minimum value, will possess minimum value. And if we can solve this problem, we can get this F. And now our training, so we call this as a training phase. And we get this phase, F, the filter, and we go for testing of this filter. So we can just take these filter coefficients and we can implement in the as an instrument, separate instrument for that. Now, as I said, that F can be linear. So what is that if I think of that linear one? So what is that situations what actually we're doing? So by solving this problem. So you can see that we have an ideal phase detector which can detect every phases, right? So this xi and which is producing this y equal to 1 to 0. And then we have this filter. Now we have replaced that h by this symbol w to make it generalized, and we'll try to relate it with the further development. And so this w, so what we want to find this w, and we have this desired one. So essentially the structure, if you have experience with any signal processing course, you can identify that this is essentially a system identification problem. And so we are trying to identify that system. And now once we find this W, we replace this ideal phase detector and we take it as an instrument to for any phase to be detected from the images. Now, since we are regarding this as a linear filtering problem, what essentially is needed that whether the Xi's are correctly identified, correctly labeled by this machine, by this filter or not. And if it is correctly doing, how much it is accurate. So that means the accuracy of that filter output should be checked. And so that accuracy can be identified with what we call that ROC curve. And what it does is that it try to find the true positive rate versus this false positive rate, or sometimes it is also used as a precision recall curve, and essentially the ideal condition must be the curve must be as high as possible. So the area under this curve, which we call AUC, that must be closer to 1 or 100%. Okay, but it is definitely not going to give you that one in reality. And so, because you can see that's the same problem if we try to identify the geometry of this. So we can find that because of this error introduced the noise. Okay, so we can have some noise. So the signal space is this, but the observation vector or observation signal will be this, which is out of the signal space. Okay, and so there will always remain a minimum error. So this is unavoidable, right? And so this error we have to accept, and therefore we never be able to achieve 100% one with so many image databases or so, right? And so we can observe that this linear operator, which essentially does this linearizations around the operating condition of this classification problem, which will not give us 100% accuracy, or let me which is required for us. Okay, so so what we can go, we can do it with a nonlinear filtering. Now, what this filtering was doing, this output essentially is W transpose this Xi, right? So it's a linear projection on this space. Now, we can see here that W transpose Xi component is there. Along with that, some bias term is given just to adjust these errors, or means in this complete cycle. And then we have also introduced what we call it as an activation function. And that is denoted by the sigma. And this is essentially a nonlinear one. Okay. And so we are linearly projecting the signal into higher dimensional spaces, and then we are adding some bias to that to adjust the, say for example, some null situation that input is 0, output must also be 0, and then we are applying a nonlinear functions into it, and then we are calculating this, all these. So these remaining operations will remain same. Only thing is that this filter f is now this operation. Okay, so we can identify that earlier we had this, it means wide usage of this function, sigmoid function which is nonlinear in nature, right? So we want now that this given this x, the examples of these, this y hat is nothing but the probability that y is 1 with the condition x is already given to us. And so since this is a probability, so it must lie between 0 to 1. And then we have this y as this one. So what does this mean? We can see that we have this z. So z is nothing but this y hat now. And so depending upon this y hat, we can have either 0 or 1. So maybe we can get some y hat at this location. So y hat is equal to 2. And so correspondingly, we can get the actual y hat. So sorry, this is not y hat. This is the variable that W transpose xi plus bi. So that variable, and that found to be true. Audible yet? Am I audible?
Yes, sir, you're audible.
Okay. So this z happens to be 2, and corresponding to that, this is say 0.87 or so. And so if it is say more than 0.5, we can say that this is a phase. If it is less than 0.5, say somewhere here, so it is non-phase. So our objective is to define that cost function or the loss function as this one. And if we do so, we can find that if it is say 1, right? So this value is to be this loss functions will be, this is means this is actually given the function face image, and now this is also, this is 0, say for example, so identified as non-face, or say this is some value, say or 1, whatever it is. So depending upon that, so if it is 1, then this component is off, and if it is 0, then this component will be on. And so we'll get either that phase component or the non-phase component, and this particular loss function will give weightage to them. And then we have multiple such images, so we can have this m number of image example which contains both phase and non-phases in this set, and we carry on these operations, this finding this W. So we want to find this W, we want to find this B, and this sigma is decided as per the context, right? Now while the sigma is called as this sigmoid function, but in general we can think of any nonlinear function here, and so our cost function is dependent on this. Now for minimizing this cost function with respect to this W and B, so definitely we want to find the partial differential along this W and this B. And so this will be computed to find the steepest descent method. We can imagine that our cost function is a convex one, and then we can have a minimum point somewhere here, and so we want to update these w's, and so we can get this n plus 1 as n, then minus half, say mu sums 1 into this grad j w, and then we have this bn plus 1, so this bn minus say half mu grad j b, and so we can find with an iterative approach at what point means for what values of w's and b this will give us this cost function will be minimum, and then we'll set those w's and b for this filter, which can help us to identify this operation. So that means it will produce this y equal to 1 for this and y equal to 0 for that, right? So we can move to find that so far what are the different developments happened along this or for this object or non-object. So we are just not identifying or finding the phase versus non-phase, but we can introduce this object non-object development, this binary classification problem. And so we can find that the beginning, so this lines you can see that shift, which is a feature, and to find that feature we have a particular operations. Okay, so we can say that fixed operation, just like Fourier transform. So shift is also a transform, and so it gives or so we can able to visualize the same image with different domain in different domain, and that will be describing that image, and particularly say that particular object has certain shift values or distribution of that shift values, which is different from the shift value of the non-object. And so we can distinguish the object and non-object with that fixed operations features. Okay, and there are again this Paul Viola, which became very common or popular in that, which has used this R wavelet transform to this identify or distinguish between two objects or identify a particular objects. But in all these cases, we can observe that these are fixed feature descriptions. That means we a priori identifying a particular feature that it can give, and we are assuming and then experimenting or testing and finding that whether these are giving the distinction between two objects or not, and if it is prominently giving that, so we can utilize that one. Later on what happens, and particularly that would be suitable for the user, right? So for the user who doesn't know much about the features and doesn't want to say intervene into much the mathematical requirement of finding those features or so. And so being an user and particularly not understanding the mathematics in depth, so we do that operation? So that means the machine has to do it, right? And so there is a development which is actually trying to identify the feature from the data itself. So this is again analogous to the situation that we can have the Fourier transform where the kernels, the basis functions, that is e to the power minus j omega t, which is known to us a priori. We are only taking that dimension on this e to the power j omega t. So this omega is varying in different dimensions and we are representing the signal. But sometimes we also go for eigenvectors, right? And so that we create. So from say this one. And so that we obtain from the data itself. So we are learning the dimensions itself, and that we will be calling as a learning the feature in this case. So here we are learning the features adaptively, while in this case we have fixed set of features. Okay, and so we can find in these that we have predefined features in all these development. These are features or shape, then combinations of these, and then we can do that. All these are that filter, what we had discussed so far. These are also filter, but implemented in different way, that we have these two-stage object detections here, that localizations and detection are combined, and in other cases or it means it is combined in two stages. In other cases it is combined in the one stage only. Okay, so that same thing. So that is L plus D, and this is combining one operations also. But what we have to observe here, that the prior development consists of predefined features, and then one question comes here, that what are the suitable feature to distinguish different objects. And because of this question, there was a huge of work for what we call as a feature selection. So the feature selection was a massive task, which we find that it requires a lot of computations also, and a prior knowledge about that image or so. And so we move to certain domain where these features are automatically getting selected. So we don't have to means identify or select the features a priori, but it will be extracted from the data itself. And those, what are those features? What we have observed earlier, that these edge features or the part of the faces or the full face, which can connect these atoms of those faces. Okay? And so this is essentially will indicate that we need a pre-processing, then feature extraction, then feature selection, and then we can go for identifying that. So after that, we find that if the filter. And in this case, all these process combined with these deep learning models. Now, out of that, this feature selection, feature extraction up to that part is essentially we'll be observing that it is called the convolution neural network, which is extracting the features, identifying the features, and selecting the features particularly for that particular object during the training session. And then we can go for identifying this f dot also, and then f dot is replaced by this deep learning plus this CNN. So it's not just a DNN, but it's a combination of CNN plus this DNN, deep neural network. So essentially the CNN helps us to identify the features, extract the features, and select the features for particular objects, like say this cat, and then we want to classify them. And so this is automatic one. So we see some examples with the predefined features. Particularly, we have chosen the popular one, which is the Viola-Jones face detector, right? So here we have this R classifier, which is actually, you can observe in this video, that these particular black and white dots that is getting uh, moving on to these images at different level of resolution. So, and then they are computing. So this is just nothing but the inner product between these particular features. So we can identify this feature as with a matrix with values that say these are zeros and these are ones. Depending upon the size, we can have either means this size. So we can have say k cross k. Okay. Although the image we are having a different scale, and all these scales according to that scale we decide this window, and then we can compute these. So we place this feature on the image and multiply this, we do the inner product. So if I denote it as this, so the output of that will be the inner product between the image at different level with the kernel, say KH or R. So that would be our feature here. Okay. And so this feature, so it will form, so now this will form a space. So this dimension corresponding to this, and say for example this rectangular dimension. So let us identify this as say uh, RS, then say this is RR for rectangle, and so this is my RS dimension, this is RR dimension, and so on. We have number of such uh, shapes of the R classifier. So if we see this in single dimensional view, we'll get like this in one. In another, we can see like this, or in another, we can see like this. So with different such shapes. And if you try to find an analogy with the Fourier transform, these are the basis functions for this R classification problem. So this forms a R feature space. And in that space, the image which contains these spaces may assume certain locations, say for example. Okay? And the non-faces can assume the other locations. But because of this, no system is 100% accurate. So this feature may not be 100% exclusively distinguishing between the face and non-face. So we can have different points which are non-face within the cluster of the faces also. And then our task is to find a boundary between these. And essentially, this boundary is nonlinear in nature. And this boundary can be learned. And so That means it requires a training, right? And so these are all, so we can identify these as face image and these as non-face image. Okay, so we want to find this boundary between these points. What are these points? These are the hard feature point. How do we get that point? By inner product operations on this image at different level of resolution. So multi-resolution operations. And so we can go for different scale. We can identify the images at different scales and then we concatenate and combine this. But so this was actually developed, this hard feature, by Professor Pawan Sinha of MIT, which was actually termed as ratio template. But later on, the computations of this hard feature requires a further working, and that work is done by this Paul Viola and Jones. So what they have done essentially, they have tried to develop a computation strategy which will ease the computation of our hard features. And that's how they introduced the term called integral image, and which is nothing but the sum of the pixel in this direction and this direction and placing at that corner positions. Okay, and so we can see that for the 1 it is 1, but for this 1 plus 1 2, for this 1 plus 2 plus 3, for this fourth one, so it will be all these pixel value 1 1 1, and so this is second one, so this 1 1 1 1, so this 4, and that is placed on this. Now how this is giving us, so these are the different examples of hard features which should be computed from these images, and we can get some time complexity, that means the resource utilizations as well as the computation time requirement for that. Now we can see that how these integral image computations are helping us. So say for example, we have this value A, this value as D, and this C and B, and we want to find the hard feature. So we can find that hard feature rectangular sum using this integral image like A plus B minus B minus C. And so only this one adder and two subtraction will help us to find the same one without this integral image operation. And so this way we can find that 8 adders are required without this, while this one adder and two subtractor, essentially 3 adders are required for this, so we can reduce that one. So that was the contribution by Paul Viola to speed up the operations of these feature computations by the heart. And then we can have different means reduced outcome. And after we get these features as we have just drawn, that the images will be represented as a points in that particular hard feature space. Okay. So we want to learn it, but or to define it, this classification. So we want to have this boundary, and that boundary we can do with this AdaBoost mechanism, where this AdaBoost one is used with a weak classifier. So say for example only one dimension, along with one dimension we are classifying, and so we can identify this way that we first use a threshold and we get a boundary like this. Then we apply a threshold in another dimension and then we get the boundary. Say for example, this was face for this H1 and for this H2, this region was face. And so we can get that these regions are non-face for the non-face. Okay. Now you can if you recollect your experience with our coordinate geometry, that a certain point is which side of the line those points are there. So you can find this is essentially the same thing we are doing. So, and then we are clubbing all these effect of all these weak classifier and then finding a zone beyond which the face may lie or within which the non-face may lie. And so essentially, we are trying to approximate this boundary, so approximating the boundary using a small boundary, linear boundaries. And that's why we're calling it as a weak classifier. And then we are trying to combine this and find the overall boundary of the system. And so we go with different resolutions level as well as this weak classifier, then we are combining. So as we are moving through the cascades of classifiers, we are trying to reject some of the inputs, region of the images, and some of the region of the images are ultimately detected as the face. And so what we observe here, that this hard feature is computed, hard feature is a priori decided, that we observe that what happens on the facial images. So when the light is illuminating over the faces, we can see that maybe white depending upon the illumination orientations or so. And then it is essentially that black white. So what I am trying to convey, that we have this nose and these eyes, and because of illumination this may be the black one. So while this is black one, so the low light conditions will be there, and if I combine this, we can have white region. It is essentially similar to that hard feature, three rectangles are wavelength, right? And so, and now, so what we are essentially using means why we are using these hard features, because we are finding the distributions of the illuminations of the faces, which can be described as a linear combinations of these wavelengths. And that is the reason why we have chosen this. But whether it is the best one, so we cannot say, because we can only say its limitations, and that by the term that area under the curve of the ROC, and so we can find, and this is not the 100% accurate, so we can have still scopes to improve that one. And so the alternative solutions we can find that adaptive one. So adaptive feature-based solutions, which is basically require that learning of the feature itself. So as I said, already highlighted that part. And so we can start with a shallow network. That means only one operation or one layer is there. And then we can go with these examples, minimizing that with the number of examples of the inputs x1, x2, xn, and so on. Now, if we extend this concept, so each of these operation, now we are placing in the different layers and the nodes of those layers, we come up with a deep neural network if we increase this number of layers. Okay, and so we are doing the same operations, but now this is repeatedly doing to have different orientation. So it is like if I want to observe certain scene through a camera, so I can my camera around 360 degree and get different view of the same object. So similar to that, with that concept, we go for these different layers. And then every layer. So these will have these parameters to be learned, and this will also have these parameters to be learned. So instead of learning that or approximating that, this boundary which we have observed just now, so we are doing this WB and AWB. So all these we are learning. So this learning is essentially related to the same, that classification boundary. Fine. So we can have the computations of them, like we want to compute. So all these equations actually will help you to code your neural network, the forward propagations. That means first we have to compute this y. Once we compute this y, we can go for this loss function y hat and y. Once this loss function is computed, then we can go for delta of that loss function, the parameter, that w and delta b of different levels. That means different layers. Okay, and so in this, each of these layers also contains this nonlinear operator, the sigma. So we need to understand this, means we need to have some formulations for that also, and need to understand that what will happen if we differentiate with respect to the sigma itself, these loss functions, and so then we'll move to go to this route, and we'll call it as a backward propagation, and we'll backward action or developing neural network development. And so we can have different activation functions. So today, with this trend, the many cases we can find that this ReLU, this this uh, is called this LU, linear unit. So rectified linear unit, which is A, which is maximum of this 0 and Z. So majority of the cases you can observe that the hidden layer, the layer inside this input and output, yes, those are using these ReLU operations or the functions. And depending upon the requirement, the other functions are also used. And so here, while working with these, what we have to be very careful on the dimensions of each layer and so on. And if we have can make it correct, we can get the correct output. So this particular diagram is showing that we go for forward propagation. Once we have done this, then we can come back to this backward propagation to find this derivative of that. So all these, although we have written dz, db, dw, it is essentially meaning that it is del that loss function with respect to del wl. L is the layer number. And sometimes you may find the indices like with the first bracket, which is the example image, means index for example images. So with this forward and backward propagation, we can set this W and B each and every layer, and then our job is done for the training. We can use the same thing for the testing. That means we can use this to make our instruments or so. And so once this, as I said, that convolution neural network part essentially extract and selects the features. So these are the features C1, C2, Cn, and then those features are fed to the DNS, this neural network. Okay. Now, why we want to do this? So let us see that we want to go for say 64 for 64.3. So this many pixels, if I directly put into the DNN instead of C1, C2, Cn, if I go for pixels only, So I will have this many pixels, and then we require, so let us see that calculation. For 1000 cross 1000 cross 3, we have 3 into 10 to the power 6 pixels. And so we have these one. You can see this loop. So that need to be that 1000 cross 3 into 10 to the power 6. So that many computations we need. If we directly use these pixels, so that means if my feature is identity of the image itself. So say this is phi of I, but this phi is identity. Then we have to go for this many computations, and not only that, we have to store this many coefficients values. So if we go with that convolution operations, we can see that this will be reducing. So we quickly observe that how these convolutions are carried out. So this is just spatially, we are moving the kernel, this 3 cross 3, and then we are finding that one. Okay, so similar. So we can get the edges, we can get these different. Similarly, horizontal. But what is our concern here? To identify that what happens to the output's image size. So we can see that our input image was 6 cross 6, the kernel was 3 cross 3, and we get a 4 cross 4 as the output. And these are, we'll be essentially calling the features. And so the filter output, the output size would be n minus f plus 1. Now, sometimes we want to pad this image to keep the image size same. We can do that also with padding, right? And so now sometimes we can go for strided convolution. So you can observe the difference between that earlier we had this kernel on these locations, then next the kernel would be on these locations. But with the strided operations, we are moving this kernel into say one strided, so we are galloping this 1 pixel locations and moving this one. And essentially, once we go for strided convolution, so we are getting the size, output size as this n plus twice p, p being the padding, minus f by s plus 1, then floor of that. Now, why we can employ these type of convolutions? Because the neighboring pixel may be having some correlations and can be omitted. Okay, and so, but at the same time, we'll get advantage of the encoding of these informations into smaller number of feature values. And so whatever we do in 2-dimensional, we can also go for 3-dimensional, like we want to work on the RGB, the color image itself, and therefore we can go convolutions on the volume. And then you can see we have these 3 channels here, but this is only applied to these 3 channels of the input image. And so this will generate, so the same way this volume will be placed or moved from one locations to another locations, and then without striding of the convolutions will generate the all these. So we are summing all these components here for all the channel, and therefore we are getting a scalar value for each position. Okay, and so mathematically we can observe that this is our, so we are summing all three directions, so we are getting the scalar value. And this is what we are getting. Although we have a three channels here, we are getting a single output of two dimensions, 4 cross 4, right? And so we can see now that we have this image 6 cross 6 cross 3. Then we can have a vertical edge, one feature, 3 cross 3 cross 3. But if I multiply this, I will get only 1 4 cross 4. I am adding another one, which is responsible for horizontal edge finding, say for example. And so then output of that will be another 4 cross 4 image. And so essentially, if I multiply the number of filters, so two number of filters, so two channels is generated at the output. And now, if we implement with only the pixel values, and say we have a 32 cross 32 cross 3, and then after this filter operations we get 28 cross 20 cross 6. But if we do not do that, then without that this convolution, we have this WL, which is of the size this 30 472 into 4704. So that many W coefficients need to be stored, that many computations are also required. But if we go for only this one, and what we need, we want to learn these filters. So what I have told here, that filter are already given here. Only pixels are changed to these pixels, these values. And so we are working on the pixels only. And so filter is already known to us. Now we are telling that filter should be learned and that filter will be fixed. So we do not need this image size pixels or so. We only need this W as the filter coefficients, and that will be the number of filter coefficients plus the bias for each of the filters. And so we can do the same solution with this 456 or so. This is just a numerical examples for understanding, but you can check it by yourself for the exact value or so. But this is far more reduced than the pixel. So instead of working directly on the pixel values using the DNN, we can work on with the CNN, and then we can apply this DNN. So once this feature is reduced, and then we can, if we go for DNN, then the total computations on in the DNN also will be reduced. Apart from that, we can also have that parameter sharing and sparsity of connections facilities while we involve these CNN operations. Now we can jot down, summarize these CNN plus DNN operations, what we are doing. So we are first convolving, which is a linear operations. Then we are applying a pooling layer. Will be again highlighting that what it is. But it is essentially non-linear operations, which comes under the CNN. Then we go for fully connected, which is DNN, and then we have these projections on different spaces, which is essentially that xi plus bi operation, and then we have activation functions, so that sigma or any other nonlinear functions of this. So combining all these layers will form what is phase detector network. So to have this pooling, once again, this is similar to that stride computations, but it is done differently. That we take this block of, instead of storing all these pixel values. So this is our feature points, feature values. Now, if I want to store all these feature values, so I need to have all that many locations, memory size. Instead of that, if we only take this maximum of say certain region, say I am doing on this, and then I can move this window over this image. I can have a overlapping window or I can have a non-overlapping window, but that decision will be based on the different context. Okay, so completely relating to the physical phenomenon. So for example, in certain cases, we do not need overlapping windows. We can do it by non-overlapping windows. And in that case, we can do. So we can, out of these 4 pixel, we can only store the maximum values of those feature values. So that pixel by that word means I mean that feature values. And so instead of taking 16 coefficients or 16 weights, you can say, we are only keeping on these. Now, why this will work, this may work, because we can see that this can be the maximum deviations from these, or so this can be a representative value for these features out of this set of features. And so essentially again it is an encoding of that, and that maximum value will have may have a maximum distinction or between the other feature values of other objects. And so we can combine this pooling layer and convolution layer together, okay, and we can find those convolutions. So once that convolution is done, we can find the max pooling, or sometimes we can go for average pooling. Okay, so that completely depends on the context. And then we can have the hyperparameters that filters size, the stride, or then maximum or average pooling. Depending upon that, we can find the output size. So once that output size, you can see gradually we are decreasing. So all these decreasing, and these two can be that DNA. So up to that, we have reduced the features. So number of pixels, instead of number of pixels, we are taking the features. And here we are putting direct pixels. Okay. And then we are collecting the means stimulating those by those features to this DNA. So this is, we have already said. Now you can understand that all these filter coefficients which are involved in CNN plus these DNN weights, so all these are to be stored, and so that memory requirement will be there for all these. But you can see also, analyze by yourself, that you can find that this is actually essentially reducing the number of computations and storage requirement. Now to make it further, we can go with a hardware accelerator. And the approach is, or could be visualized like this, that we may have a processor like system on chip. And then we have this programmable logic unit where we can define our hardware, and we can call them as a intellectual property core, IP core. And then we can have a communications between this IP core and the processor. So this processor can be any sort of say microcontroller which that particular manufacturer are providing in that. So for example, in Zinc, it is the ARM processor is there. Now, some part of your overall work can be carried out in the microcontroller, and some part can be carried out in this IP. Now, why we should go for IP? Because some of the operations inherently we can find that concurrent in nature. That means so if I go for the same solutions or same problem computations in the ARM or the microcontroller, it may take longer time because of the sequential execution nature of this processor. While the algorithm itself may have concurrent operations, and we can exploit that by developing these IPs, right? And so we have two situations here. One is the software. We can write a software for this programming section. Okay, that means this microcontroller. Some people can use assembly language of that particular microcontroller, or sometimes you can write with a high level language like C or embedded C or something like that. And then for developing this IP, you need another descriptive language, this Verilog or VHDL or so. This is essentially making one hardware. You can think, you can visualize that way. And so our target is to make an hardware for the CNN. So we want to develop a CNN plus DNN combination, this structure, as an IP on this VHDL. So we can start with say convolution, how we can do that convolution. So we can develop a flow or diagram like this, which we can show that this is essentially the systolic architecture. So which takes this pixel sequentially but have a intermediate shift registers, storage, and computing this. Now each of these pads you can say are the multiplier and adder block. Okay. So on the next slide, it will be visible. So we can see from here that these pixel values are moving this fashion. And then we can have all these computations done here. And this can be further taken for the further operation. So these pads can be mapped like this. So we have this operation. So this is one pad. This is another pad and like that. Now this can be implemented as a distributed arithmetic system like using the CLPs in Xilinx, or it can be implemented in Mac unit. Okay, so this is essentially convolution unit, which is hardware, and we can do that appending with this many delays, which are essentially the shift registers in. So this particular architecture will help us to go for convolution. And for max pooling, we can have this structure like this. So we can have, so this is our feature. So input matrix, but this is feature values. And then we can have the movement of the those features through this. And then we can have this output as 5 because this line is 2. And so we'll get the output as 5 max, which will be passed for the other operations. So now we can again see, recollect that one, that how our DSP neural network, and then it is, so now at this moment, we get the feature value reduced, much reduced than these pixel numbers, and those values are rearranged to put it in the, for the DNN, and then we generate this Y hat, which is again used for finding the error, and then minimizing that error will decide these filters. So these filter coefficients will be updated, and all these weights W's are also will be updated. Then in the fully connected layer, that means that this DNN layer, it is again the input vector is getting multiplied with the weight matrix. And so we can have some registers or buffer to store this feature vector after the last computation layer, and then we go for this computation. So these are only multipliers and adder combinations. So we can do it for different nodes at different layers of the fully connected layer. So to understand the design performance, that means how good my system is, and what are the main issue here is that in this small resource or resource constrained system, we have like this ZC702. So we have limited resources like these LEDs, these LED RAM, these electronics, and so we need to check that combining all these structures. So we have done it for, we will be seeing that for fully connected layers. So we can see for the image size of this many resources are getting utilized, which is much below than this. So this is for the max pooling layer, and this is for fully connected layer. But this you can see that we have two layers. So if we identify, so we can at the simulation level itself that how far we can go, how many layers we can go. So with that, we can confine our utilizations within this, and then that would be our limitations, that how many layers we can implement in that platform. So, and then accordingly our performance will also vary, or it can vary. So one performance is the resource utilizations, and for particularly for resource constraint environment, we should be aware of that. And then the other is time. But for that, we are generating the AI where the concurrency of different processes as well as the data can be exploited. And so we can, which actually if we implement it in the, say, sequential processor would have taken number of clock cycles. In IP, it can be done, say, with reduced number of clock cycles or so. And this is some representative references. And okay, that's it from my side, Vipin. And if you have any queries, we can have some discussions on
Thank you, sir, for such a detailed and wonderful session. Participants, any queries are there, you can unmute yourself or type in chat box. Sir, I guess there are no queries. So thank you once again.
that. Okay.
On behalf of Triple IT, I thank you for taking out time from your busy schedule and giving this informative session to us. Thank you, sir.
I hope that
Sir,
will be useful for the others. Yes.
Yes, sir.
hello. So, is it possible to
Uh,
get your PPT, sir?
I
Hello.
think Vipin need that one for your official requirement or not?
Sir, on our portal, we means if they ask to upload, I will contact you for that. Currently,
Okay.
Miss
Okay.
AICT has not put that requirement as of now.
Okay.
But sir, all the sessions recordings will be there on YouTube, so participants they
Yes.
can
Yes. Yes.
rewatch all the sessions.
Yes. Yes. Yes.
Okay.
That would be better.
Yes. Thank you once again, sir. I am closing this meeting.
Okay. Okay. Thank you all.